All right, the last section we're going to look at is, the last part of it is 4.2, part 2. And yesterday we looked at graphing functions when the degree of the numerator was less than or equal to the degree of the denominator. So that's what we did yesterday. Right. Today, what we're going to look at is when the degree of the numerator is greater than the degree of the denominator. And when the degree of the numerator is bigger, we can get some different kinds of things that happen. In general, we don't want them to be too far apart. All right? The closer the degrees are, the better, easier. If the degree in the numerator was like a 7 and the degree in the denominator was like a 2, that's going to be pretty bad. All right? We're going to have it's going to be a tough one to graph. So ideally, we don't want the degrees to be too far apart. And I'll probably give you one at most that would be 2 degrees apart. But that's what we're going to take a look at today. And whenever the degree in the top is bigger, we have this new type of thing that we can find called the EBA. A little different than the EBM. EBM is easy to find. All you have to do is highest degree term in the top divided by the highest degree term in the bottom. The EBA is found by doing long division or synthetic division. So let's say that we had 2 polynomials and we're dividing them. Right? H of x over g of x. When you have a problem, it could be something like that. 2x cubed minus 4x plus 3 would be the top, and x minus 2 would be your g of x. Remember that when you divide them, you're going to get a quotient and you get a remainder. Right? Even if the remainder is 0, you still have something. So when you divide them, you're going to get a quotient and a remainder. And remember how I said we can write our answer. You can write it as quotient plus remainder over your original denominator. It's just another way to write an answer when you do long division. And we talked about that back in chapter 3. Well, the EBA is just the quotient part. This part becomes unimportant when you're looking at the EBA. Because think about when you divide, like let's say you had a remainder of 3. And let's say you were originally dividing by x minus 2. Right? So let's say you had a quotient plus and your remainder was 3 over x minus 2. What happens to this fraction as x approaches infinity? Nick?
It approaches 0.
It approaches 0. So this part that I have circled, when you put your remainder over your original divisor, your divisor is going to have a variable in it. And if a variable in the bottom, in a divisor, in the bottom of a fraction gets really big, it causes the entire fraction to get really small. So as you approach infinity, this part becomes insignificant. It becomes almost nothing. So the only part that's really important is the quotient. And that predicts what your graph is going to look like at the ends of the function. Now, the behavior can get a little bit more complicated than just a horizontal asymptote, and that's what we're going to look at. So we've looked at 2 cases. If you have the case where the degree in the top is smaller than the degree in the bottom, you could end up with something like 4 over x. That's an example of like an EBM from last night's homework. In that case, you had a horizontal asymptote at 0. If the degrees are the same, like 2x squared over 3x squared, degrees would cancel and you still get a horizontal asymptote, but it's not at 0. It's up at 2/3. Okay? So yesterday, our end behavior was either a horizontal asymptote at 0 or a horizontal asymptote at a number. It's not necessarily going to be a horizontal asymptote today, when the degree in the top is bigger. And let's start to see what happens. So let's find out some things about this graph, and we're going to eventually graph this problem. But let's find out a few things first, and then we'll use those things to make a sketch. All right. So how do I find the EBA? It's just the what? Yeah.
You divide it and then you find the remainder over the original equation. Or the geometry.
So is that the part that I want, or that's the part that doesn't matter?
Oh, sorry, I know you want the quotient.
I want the quotient. That's the part that's important. Can I do synthetic division with this one?
Certainly not.
Why not?
Yes, you can.
Yeah, I can. So let's just put a 2, and then go 2, -4, 0, 3. All right, let's get our quotient. So 2 times 2 is 4, -4 plus 4, 0, 0, 0, 0, and the remainder is 3. So, what do they want to know?
Why wouldn't you put -2 for?
Because it's always the number after the x minus.
Oh, okay.
If that was x plus 2, then we would have put minus 2.
Okay, thank you.
So what's my quotient there? 3 is my remainder. Maybe 2x squared.
Is it double squared?
Mm-hmm.
Was it the original term cubed?
Constant, linear, quadratic. So that's the coefficient of the quadratic term. There is no linear and there is no constant in this one. It just came out to zeros. So 2x squared. What else do they want to know? Remainder. What's my remainder? Well, I think I just said it. What's the remainder? 3. And the EBA. What's the EBA?
And Hager asymptote. 2x squared.
2x squared. And we already talked about this question. What happens to your remainder as x approaches infinity? It approaches 0. Right? If you write your remainder like this, take your remainder and put it over your original divisor. As x approaches infinity, the remainder really doesn't matter because it becomes infinitely small. So that's what happens to the remainder. It approaches 0. So, there's a difference between the EBM and the EBA. Okay, the EBM is what we learned yesterday. That's when you take the highest degree term in the top and divide by the highest degree term in the bottom. Sometimes the EBM and the EBA could be the same. Sometimes they could be different. It depends. But the EBA that one takes a little bit longer to find because you have to do out long division or synthetic division. And in the problem we just did, the EBM here would be 2x squared, and the EBA is 2x squared. And that only happened because these both came out to zeros. Just the way it worked out with the numbers. If I changed one of these numbers to be like a 2, now you're probably not going to get zeros in both of those spots. So the EBA would probably have a constant or a linear term, where the EBM wouldn't. Okay. So in the kind of problems we did yesterday, the degree of the numerator was always less than or equal to the degree of the denominator. That means we always had straight line asymptotes, either verticals or horizontals. The horizontal could have been at 0, or the horizontal could have been up at a number. But those were the only 2 cases you could have had for horizontal. When the degree in the numerator is bigger than the denominator, the horizontal asymptote goes away. You don't have the horizontal anymore. You could still have verticals. But what you have instead of a horizontal asymptote is an EBA. That is going to take the place of the horizontal asymptote. And depending on how far apart the degree is in the top from the bottom, the asymptote can curve. So you can have a curve that you're getting closer and closer and closer to. Right? So as an example, let me draw a parabola. And let's say we had an asymptote that was a parabola. In a minute, we're not even going to have to pretend because we actually do. We have an EVA that's going to be a parabola. And let's say that it looked like that. Maybe your sketch would look something like this. So the sketch of your graph gets closer and closer and closer to that parabola as you head towards infinity. So it's a curve that you're following. It's not a line, but you can see how it's getting closer and closer.
Wait, that's crazy.
Yep. So we're gonna sketch something kind of like that. Usually, if there's a part on the right, there's another part over on the left as well. It's usually two parts. Right, but that's the idea. So we can get asymptotes that are curved. How complicated of a curve? It depends on the difference between the degrees. This was a difference of a degree 2. Degree 3 in the top, degree 1 in the bottom. It's a 2-degree difference, which is going to result in a 2nd degree asymptote, or quadratic. All right, so let's take what we just did, and let's actually verify that 2x squared looks like the asymptote in that problem. So let me go back to it, and let me type in 2x cubed minus x squared plus 3. And we're going to divide by x minus 2. And what did we find for an EVA? 2x squared?
Yeah.
Okay, so I'm going to put that in. I'm going to do it as a thin line because sometimes, the pixels, when they're too thick, it's hard to see. So I'm going to do it as a really thin. I was going to do it dotted, but I'll just leave it as a thin line. I'm going to take graph. Probably going to have to zoom out to see both parts. Yeah, I gotta go higher. That's what I need to do here. Because you can't really tell that they're getting closer in this picture, but if I set the Y-max at, I don't know, let's try like 25. I think and I'll make it bigger on the screen in a second. So that's the graph that we actually have in blue. Still didn't go high enough. Let's try. What's that?
How would you do domain?
Domain, just find the zeros of the denominator and exclude those. Because there is a vertical asymptote in this problem. There is a vertical asymptote at 2. But there's also a curved asymptote that's a parabola. So I'm trying to get that part in the upper right. And I know that it should be there. Let me make sure I typed it in right. 2x cubed minus x squared plus 3 divided by x minus 2. So, why are we not seeing the other part of the graph?
Wasn't it a 4?
What was it for?
Oh yeah, it was
It's
4x
cubed.
squared.
Oh, did I erase something? Oh, that's right, I erased it. Because I changed it and I said, oh, if you change this number, that would, yeah, it was a 4. Okay, that makes more sense. I knew something was not right with what I typed in.
Mr. Hager was freaking out. He's like, what's going on?
Because there's supposed to be another part of this graph over here. Whenever you have a parabolic asymptote, you get something that has two parts. All right. Now the red line is going to look like it's tracing the blue one very closely. And let me make it bigger so you can see it. All right. So that red line is an asymptote. As you go up to the right, you can see it getting closer and closer to the blue one, but it never actually will reach it. And as we go to the left, the red and the blue are getting closer and closer and closer, and we only have so much resolution, so it looks like they're right on top of each other. But they're not. They're just getting closer and closer. I can't draw my line any thinner for the red one, so that's why it looks like it's touching it. All right. So we're going to try to figure out how we would sketch something like this by hand, and it's very similar to what we did yesterday. Okay, we're going to plot some points. We're going to put in some asymptotes, especially the vertical one. That's going to help us to have that, and see what we can do. All right. So let's use the information we have to make a sketch. We know that there was an EDA of 2x squared. I want to graph that. So I'm going to graph it. I need a few points to graph that parabola accurately. If x is 0, what's y? 0. What about if x is 1? 2? What about negative 1? 2? Let's do, what about 2? 8? Negative 2? Now, the problem is we're going to get pretty big all of a sudden here. 3 gives me what?
16.
What is it?
18.
18. And negative 3 would also be 18. We might want to do 2.5, but I would need a calculator for that one. All right, so we've got 0, 0. I'm going to make the graph smaller because it's easier for me to draw smaller and then make the graph bigger again by zooming in. 1, 2. Notice I scaled my axes because I need more space. Negative 1, 2. 2, 8. 2, 8. And then negative 2, 8. And 3, 18. So 3, 18. And negative 3 up at 18. So this is going to be an asymptote. So I'm going to draw it connected, but then I'm going to change it to a dotted line after. Again, if I make it smaller, it's just easier for me to draw. So let's draw our parabola and make it dotted. Right, so that is our asymptote. Okay, let's do the vertical asymptote. What's the vertical asymptote in this case? Yep. 2. It's the 0 of the denominator. So let's put another dotted line in at x equals 2. So what this usually does is it creates a little area that's trapped between two asymptotes, and you usually end up sketching in that tiny section. All right, and again, let's make that dotted so we remember it's an asymptote. All right, now we're going to plot some points. We're going to plot some points near this vertical asymptote, and we're going to plot some points near this red one. So I'm going to just keep trying different values for x and plot a bunch of points. Let's start with a couple points near 2. Okay, a number just a little bit smaller. 1.99. We are at negative 2,000, negative 3,000. Okay, again, don't look at the one in red. We're looking at blue. That's the actual function. So just before, you're way down here. Now, just after it, let's go 2.0001. We're up at 30,000. So we're going up extremely high. Now, I'm going to need a lot more detail about what's happening in that spot right there. So what I'm going to do is I'm going to try 2.5 and see if I can get another y value. 2.5, I'm at 18.5. So 2.5, I'm at 18.5, maybe about right there. Let's do, it's going to be hard, but let's try like 2.7. All right, kind of at the same spot, just a little bit higher. So it's going that way. And then if we try like 2.9, not 29. 2.9, I'm at 20. So as I head a little bit more to the right, now I'm up there. So what's happening is this has to stay very close, and all of a sudden it's going to curve and go through those points. And the right side of that black thing I just drew is going to be getting closer and closer to that red dotted line. So any questions on that section just by plotting 3 or 4 points? All right. Now we need to figure out what's happening in like this whole area. What does my graph look like there? So what would be another good x value to try? That would give me some more information. Yeah?
Do you want to find the x-intercept?
We could try to find the x-intercept. So we could set y equal to 0. Unfortunately, that's a cubic I have to solve. So since it didn't tell me I had to find the x-intercept, I'm probably going to hold off because that would be kind of hard. But what other intercept could we find that would be easy? Yep.
0?
Yeah, the y-intercept. Just plug in 0 for x, and you get -1.5. All right, so 0, -1. Oops. -1.5, I think would be right about there. Because remember, I'm going by 2's. Okay, so, all right, so we got that one. What would be another good x value to try? Nick?
18.
Oh boy.
Oh yeah, we're doing it now.
That's up
Scale.
at 650.
Oh, I thought we were doing it at scale.
Yeah, I can't graph when x is 18. I would be like over here, and I would be like way up there.
So -3.
Yeah, -3. I think that would be good. If you type -3, it's even better. 17.4. So -3. 17.4. Probably just above 16. Right about there. All right. What would be another good x value? Yeah.
1.
1. I kind of know what's going to happen here. It has to stay very close to that. My question is kind of like, well, what's happening in there?
Right.
Because it's going to curve at some point and then go down. So let's try 1, -1. All right, so 1, -1 would be about like that. I would do 1.5. Let's see where we're at there. -1.5. So 1.5, -1.5. All right, now I'm starting to see what's happening here. It's coming down, getting a little further away from the asymptote, and then it's going to have to curve through those points, and then go down and get closer and closer to that dotted line. And that's what your sketch is going to look like. So if we hit graph, we can see that we did pretty good. Right? Kind of comes down, does this little curve, and then it almost drops straight down, vertical asymptote. And then there's this other section. You can't see as much of it because I remember I set my Y max, I think it's up at like 50 or 40. So I had very little space to draw because my y-axis wasn't high enough. But I had just enough that I could barely get it on the grid. Okay. Any question on that? So that's a pretty typical parabolic asymptote kind of problem. Right? It's like a parabola that wants to connect, but it's like somebody went in right here and cut it. And they basically broke it off and then bent it down, and then the other section of the parabola continues up at the top. So if you zoom out enough, the graph in blue kind of looks like a parabola, but it's like broken in the middle. It's like one end bends down, and the other end that tries to connect, somebody took it and bent it up to infinity. That's basically what's happening there. It's like bending it opposite ways. All right, any questions on that? All right, so that's what we call a parabolic asymptote. Now, let's look at this one. So we want to sketch it. What's the degree in the top here? 3, and the degree in the bottom?
2.
And that's a difference of what? 1. What was the difference in the last problem? It was 2. So this is only a difference of 1. So let's see what kind of asymptote we get this time. Can I do synthetic division with that? No. So we have to do the long division with this one. So x squared plus 2x minus 3. And we're going to divide that into 2x cubed plus 7x squared minus 4. And right now, we're just finding the EDA. I could do the vertical asymptotes without doing this first. Okay, but I like to get this out of the way because it takes the longest. All right, what do you get if you divide x squared into 2x cubed? 2x. Multiply it back out. Caleb, what's 2x times x squared?
2x cubed.
2x cubed. Madison, 2x times 2x.
4x squared.
4x squared. And Sophie, 2x times negative 3.
Negative 6x.
Negative 6x. Oh, one thing I should do here. If you remember, and I caught it before we got any further, you should always fill in zeros for your missing terms. All right, so we're good. And now, Maddie, what do I do with these columns?
Subtract.
Yep, long division, you subtract. That's gone. 7 minus 4 gives me 3x squared. What's 0 minus minus 6?
Plus 6.
Plus 6. And then bring down your last term. What's 3x squared divided by x squared? Lindsay?
3.
3. Multiply it out. 3x squared. 3 times 2x, Annalise?
6x.
6. Got my x. 6x. And 3 times negative 3 gives me, Nick?
Negative 9.
Negative 9. Subtracting, that's gone. 6x minus 6x gives me 0. That's gone. And negative 4. We don't even need the remainder. Remember, the EBA only needs the quotient, and we're done. So you don't even have to worry about finishing it for the remainder. All right, there's your EBA. 2x plus 3.
Is the EBA and the quotient always going to be the same?
Yes, that's how you find the EBA. It's the quotient. What kind of asymptote is that? What kind of line? Yeah.
A linear line? No.
All lines are linear.
Yeah.
Yeah.
a straight line, not a whack.
Yeah, well, yeah, it's not a curve, but it's different than a kind of line we've had before. What? Can anyone be more specific about how this line would look? Yeah?
Has a slope of 2.
Has a slope. Yeah, has a slope of 2. So this is going to be a line that's on a slant, right? Not as bad as a quadratic asymptote at all. But let's put this in. So we've got a y-intercept at 3, and we're going to go up 2, right 1. Okay, I'm going to do it a bunch of times just to get a pretty good sketch. All right, that's probably enough. And now let me zoom out. That'll make it easier. And let's draw in this slanted line. Okay, and this is called a slant asymptote. About like that. this a little bit. That's pretty good. All right, let's make that dotted. Zoom it back in. All right, so we've got a slant asymptote. What else do they want us to find? The vertical asymptote. Okay. How do we get vertical asymptotes? Oh, maybe.
Find the zeros.
Yeah, 5 to 0 is the denominator. So x squared plus 2x minus 3. Set that equal to 0, and let's see if we can factor it. Tim, what do my signs have to be here?
Plus and minus.
Yep, need a plus and a minus. I would try plus 3 minus 1. Let's see. X squared minus x plus 3. Minus 1 plus 3 is plus 2. Perfect. So, Julie, where are my vertical asymptotes?
-3, 1.
Good. -3 and 1. Let's put those in. I'm going to make it like this again. All right, let's go -3. Close enough. 1. That's not that good. Okay. All right. And you basically have 6 sections here. Again, just like if this was horizontal, you get almost like, kind of like a tic-tac-toe board, but you get these 6 sections where you have to figure out what's happening, and usually you only end up drawing in 3 of them. That's pretty much what's going to happen here. We're really going to end up drawing in 3 of these sections. So let's plot some points. Okay, that'll help us figure out what's going on. All right, so 2x cubed, I can keep that, plus 7, so plus 7x squared. Let's make this minus 4. And divided by, I gotta fix all that. So x squared plus 2x minus 3. All right, what would be a good x value to plug in that's just to the left of my first asymptote? John?
Is that -3 the first asymptote?
Yep.
So it would be -3.1.
Yeah, I'll go -3.01. And we are at 1,246. So we are up extremely high. Now, what would be a value just to the right of that asymptote? Bob, feel it?
-2.9.
Yeah, so let's check that out. -2.99. We're at -1,253. So way down here. All right, next asymptote is at 1. Madison, what would be a good value to check near 1?
0.9.
Yep, I can go a little closer, like 0.99. We're at -120. And how about, Sophie, another good value?
For the left of it,
We did to the left of it.
or the right?
Yep,
Is that one right? Is it that? Is it the vertical asymptote is at 1, correct?
yes.
So 1.0001.
1.00001. Bless you. And we're up over 12,000. Okay, so very high. All right. I'm not really sure what's happening here. I have no idea what's happening in that middle section. So I'm going to check a few more points. Let's check 0. 0, 1 1/3. Okay, so that's another point in the middle. Let's check -1. See where we're at. -0.25. Okay. I can kind of see what's happening now. We have to connect all 4 of those dots in the middle, staying near every asymptote. So this is going to come up, stay very close, start to curve, go up like that, and then come down, getting closer and closer to that green dotted line. So that's what the middle part is going to look like. Now, the part on the left, I'm going to get a couple more points. Let's do -1, -2, -3. Let's do -4, just to get another point. -4, 4. Okay, 1, 2, 3, 4. 1, 2, 3, 4. All right, and let's do one more. Let's do like -7. -7, -10. Okay. 1, 2, 3, 4, 5, 6, 7, and then all the way down, -10. Okay, so I can see what's kind of going on here now. Stay near those asymptotes as much as you can, but you have to curve to connect the lines. So it's going to come down, start to curve, and then get closer and closer to that bottom one. All right, now the last part, I just need to maybe get another point. I know I'm going to be trapped between those two asymptotes, but I'd like one more, maybe 2 more x values. What would be another good x value to check? Yep.
2.5.
Yeah, 2 or 2.5. I think either one is going to be fine. So 2, 8. So 2, that's 10. So that's 8. And if you check, 3, I think we're going to be off the graph. I don't think you're going to be able to do it. No, we're still on 9.4. So 1, 2, 3, 9.4, right about there. Okay, so it's going to come down, and then it's going to have to curve at some point, and then it's going to get closer and closer to that dotted line, just like that. So you plot as many points as you think you need, okay, to make a sketch. Let's do zoom 6. Remember, on a zoom 6, you're just barely going to see the bottom part of that, because that's a -10 to 10 window. All right, so we're just barely going to see it. But the other 2 parts you should get really good pictures of. All right, so here's the part on the left, kind of coming up and curving. There's the part in the middle, and there's that little dip up at the top. My curvature is not really perfect on the one on the left, but that one in red, just ignore that. That was another problem. But that's pretty good. You did pretty good on that. Okay, so any questions on that?
Could we run through one more?
Let me see what we have left, and then see if we have time to do one more.
Will we see one of these on the test?
You will have something that's not a horizontal asymptote problem. So the 2 we've covered today are a parabolic asymptote and a slant. So I may ask you, even if I don't ask you to sketch it, I might ask you, what would the slant asymptote be? So you'd have to know how to find it. Okay, but that's called a slant asymptote because it's a line, but it's on an angle. And notice there's no horizontal. You can never have a horizontal asymptote when the degree in the numerator is bigger. Easiest case scenario when the degree is bigger, it's only 1 degree bigger, and you end up with a slant. The worst case you'd have on the test is it's 2 degrees bigger, and you end up with a parabolic asymptote. You could end up with cubic or quartic or whatever quintic asymptotes, but those aren't going to be ones that I would give you. Okay.
What's the craziest asymptote you've ever seen?
I mean, I've never really looked, but I mean, you could, if you had a 5th degree polynomial, you could have something that does, behavior like this. So, your sketch could be, something that just gets closer and closer like that as you go up. So it's just kind of weird in the middle, but usually the middle is not what you're tracing near. You're usually tracing near the ends of it. And then maybe your other part of your graph could, come down and do something like this and just get closer and closer. So the middle gets weird, but the ends are really all you care about. So that's the one we'll come back to if we have time. Just tell me real quick, what kind of asymptote would you expect to find here? Yep.
Slant.
Slant. Degree 2, degree 1, that's a difference of 1. Slant. And this one would be easier than the last one because what would be the zeros of the denominator? -2, there's only one root. This one had 2 roots, which gave you 2 vertical asymptotes. This one would only give you 1. So this graph would be a lot simpler than the last one. Let's see, is this just a... All right, they just want us to graph this and see what's happening. All right, and it's to kind of prove a point about when you graph something, what can happen. So let's type this in and see what happens. So 2x to the 4th plus 7x cubed plus 7x squared plus 2x divided by x cubed minus x plus 50. All right. And we're going to do a zoom 6 and just see what it looks like. Let's do zoom 6. Well, and I want to make sure that I get a pretty complete picture of this graph. I want to understand what's really happening here. All right. If I look at it, I would expect a slant asymptote because the degree in the top is 1 degree different than the bottom. And I can kind of see that in here. There's some kind of slant asymptote in there. But is there anything in this graph that looks a little suspicious? Now it's crooked. That looks a little funny that we might want to check out a little closer and see what's really happening there. Yeah?
Looks like it's getting flat to 0.
It looks like it's getting flat. And if we were finding the roots to this, we would definitely want to check this area out a little more. So let's zoom in to that box right there. That's -3 to 1 on the x-axis. So -3 to 1. And on the y-axis, -1 to 1. So let's see if we can zoom in and check out what's happening a little closer. All right, if you were finding roots here, what are you still really not sure of, even with that picture? It's kind of hard to still tell something, yeah?
Where it actually crosses the x-axis.
Yeah, I can't really tell what's happening. It still looks pretty flat to me in that area. So now let's zoom in again. Okay, just on that section. So we're already at -1 to 1. Let's go -0.1 to 0.1. So we're gonna really narrow down that y-axis, and let's see what's happening. So I'm gonna zoom in 10 times as much. -0.1 to 0.1. So I kept the x-axis the same, but I really zoomed in on the y. So now I think we've zoomed in enough that you can probably tell how many times does it look like it's crossing the x-axis? 4. Right? What appeared to be something that looked very flat, and even when you zoomed in once, it still looked kind of flat. When you zoom in again, it doesn't look flat at all. All right? So the point here is if I ask you to find roots or tell me how many times the graph crosses the x-axis, sometimes you really have to zoom in to check that out. Any question on that? That's the only point I wanted to make with that problem. I call that kind of hidden behavior. So if you really wanted to find a complete graph, I would say you need 2 windows. You need a zoomed in window to see what's happening here, but then you also need a zoomed out window because if you zoom in too much, you just lost what's happening over here. So the standard window works pretty good to get a big picture, and then a zoomed in window works good to see that. You need both. Any questions on that? All right, so let me put up what's going to be happening tomorrow with the take home. So you're not doing that assignment in the book. So this is really part 1 of the test for this week. Tomorrow is a half day. We still have class at the normal time. So this would be due at 8:30 a.m. Eastern Time. I've done this before. On the 22nd. All right, so that's 8:30 a.m. Eastern Time. That's an E. Oh, any confusion there. On the 22nd.
Of what year?
10/22/21.
In which calendar?
The one we use.
Gregorian? Alright.
My calendar. Let's see. So it's on Edge Elastic. I think it's either 6 or 7 questions. The test is 13, and I split it in half. I can't remember if tomorrow's part has 6 or 7, or tonight's part. But you'll have, all right, 1 hour to do the take-home part. So it'll be set up so you have 1 hour to do it. You can work on it in different intervals. Like if you want to work on it a little bit and then come back to it, just don't leave your Chromebook open with it on the screen, because if you're logged into the test and your Chromebook just sits there open, it's going to count as you being on the test. So if you want to start it and then stop it, what I would do is log out of Edge Elastic, so then you're not logged in. And again, that's normally how much time you have to do a whole test, 1 hour. So I think to do half a test, you should have enough time.
Is there a code we need to get it?
Yeah, there won't be a code. I'm not going to do it for this one. If not done by deadline, then grade equals 0. You can still do the in-class part, but you have to get that done by the deadline. Okay, it's 8:30 a.m. Eastern Time tomorrow.
Might as well all take in the history class for sure.
If you don't agree to the above conditions set forth on this day, if you don't agree to the above conditions, we don't really need set forth, I'm just kidding. You can take in class at some other point, schedule a time with me. If you are in ROTC, you should still be able to get that done, because it's something you're turning in electronically. You don't have to come up to me and turn it in. But if you're going to miss class tomorrow, you need to schedule a time with me next week, periods 1, 4, or 9, to take the test, or you could do it Thursday after school. Question?
Is periods 1 for 9 is like every day of the week?
That's, Tuesdays, Wednesdays, and Thursdays would be best.
Okay.
Mondays and Fridays can be a little busy.
I'll probably be able to do Tuesday 9th period. Check my shop.
Does anybody have any questions about the test, or does anybody not want to do it online? You will need a graphing calculator. Is that a problem for anybody?
That's one funny recording.
What's that?
That's one funny recording.
Yeah. The test will open, let's see, test will open, because I want to open it at the same time, so test will open at, I'll probably do 2:40 today. PM. AM already passed. So I'll open it up at 2:40.